Hello. Today, I wanted to take a moment to focus on a discussion of different ways to express concentration of solutions. Concentrations are a fancy way of measuring the amount of solute in a given volume of solution or quantity of solution. There are numerous ways to measure solution concentration. We're going to look at a few of the more common ways used in chemistry first, by way of introducing their equations. And then we're going to have a very brief discussion of converting between different concentration units. And I'll illustrate that concept by using the same solution informations to calculate the concentration of that solution in two different units. So let's look at a few different ways to measure solution concentration. The first is mass percentage. In this case, we're going to take the mass of substance A in the solution, which is often referred to as the solute, and divide it by the total mass of solution, multiplying the whole fraction by 100%. The one caution I will give here is the mass of solution. Often when you read problems related to solutions, they don't present the total mass of solution. Instead, they'll present the mass of solute and the mass of solvent separately. And you will actually be required to add up the solute plus the solvent in order to get the total mass of solution. Just a word of caution there, that you make sure that you are dividing the mass of the solute by the total mass of the solution. Related to mass percent, or percent by mass, it's referred to either way, are the idea of parts per million and parts per billion. Mass percent, you see, is really simply parts per 100. Okay? Parts per million is the mass of the solution, mass of the solute, in other words, mass of A, or mass of solute, divided by the total mass of solution. And now, instead of multiplying by 100, we're going to multiply by 10 to the sixth. And that will give us parts per million. To get parts per billion, it's mass of the solute, or mass of A, divided by the total mass of solution times 10 to the ninth. So as you can see, parts per million and parts per billion are very much like mass percent, except we're multiplying by a different factor after calculating the ratio. Parts per million and parts per billion are pretty common mainstream concentration terms. Often you hear about parts per billion or parts per million in terms of pollutants, either in the air or in water. Another way to calculate solution concentration is the mole fraction, which is abbreviated with a capital X. The mole fraction of component A is the moles of A divided by the total moles of all components. If, for example, you wanted the mole fraction of solute in a solution, then you would be talking about moles of solute divided by total moles of solution. Another caution here, you're not going to be able to calculate the total moles of solution using some sort of odd molar mass for the solution. Instead, you're going to have to use the molar mass of the solute to calculate moles of solute. You're going to have to use the molar mass of the solvent to calculate moles of solvent, and then you're going to have to add them together to get moles of solution. In other words, this denominator is very much like the denominator you see in mass percent, except this one is in moles as opposed to grams. The most common concentration unit in chemistry is molarity. which is technically abbreviated with an uppercase italicized M, though rarely do you see the M italicized in textbooks these days. Molarity is the moles of solute divided by the liters of solution. The one problem with the molarity concentration unit is that the volume, i.e. liters of a solution, is temperature dependent. As temperature changes, the volume changes, and therefore the molarity changes. For our purposes, this will not produce significant complications. However, as you advance in chemistry, you will encounter situations where molarity is simply not an adequate unit. And as such, we need a concentration unit related to molarity that is not temperature dependent. That particular related concentration unit is known as molality, which is abbreviated with a lowercase italicized m, not to be confused with mass. Molarity, or molality, is the moles of solute divided by the kilograms of solvent. Since moles and mass are not temperature dependent, molality is independent of temperature and will not change as you change the solution's temperature. It is preferred in situations where large temperature changes are possible within the solution. All of these concentration units can be converted between. In other words, if you know the appropriate information, you can convert from the mole fraction of a solution to its mass percent, to its molarity, molality, and so on. Often, you will need a few additional pieces of information, such as the solution's density, in order to carry out such conversions. For the purpose of this presentation, let's focus on using the same set of information to calculate both the molarity and molality of a solution. The secret to converting between different concentration units is the ability to find from the given information the grams of solute, grams of solvent, and grams of solution. If you can find those three things accurately from the given information, you can calculate any of the solution concentrations we just discussed. This is perhaps best illustrated by looking at an example. The example that we're going to utilize today is a solution with a density of 1.10 grams per milliliter is 36% by mass HCl, which has a molecular weight of 36.46 grams per mole. Initially, let's try to figure out the molarity of this solution. And then we use the same given information to calculate its molality. If we're going to calculate the molarity to begin with, we are going to need the moles of solute, in this case HCl, and we are going to need the total volume of solution in liters. Because we have a percentage, 36% by mass, it is logical in this situation to assume that we have 100 grams of solution. The only reason we make this assumption is then we can also assume if there's 100 grams of solution, 36% of 100 is 36 grams. In other words, in addition to saying we have 100 grams of solution, it is accurate to conclude that we have 36 grams of HCl. That is important because now we can convert the grams of HCl to moles of HCl. 100 grams of solution minus 36 grams of HCl also tells us that we have 64 grams of water. Okay? So what we just did by assuming 100 grams of solution is calculate the grams of solution that we assumed, 100 grams. We calculated the grams of solute, 36 grams. And we were able to calculate the grams of solvent, 64 grams. Knowing all three of these pieces of information will make our life easier going forward. We're going to convert the 36 grams of HCl to moles of HCl. We're going to do that by dividing by the molar mass. So 36 grams of HCl divided by 36.46 grams per mole tells us that we have 0.99 moles of HCl. Now we need to calculate the volume of the solution in liters. We know we have 100 grams of solution. We know the density of the solution is 1.1 grams per milliliter. 100 grams divided by 1.1 grams per milliliter. And we also know that there's 1,000 milliliters in a liter. Tells us that the solution is 0.909 liters in total volume. In other words, we use the density to solve for the volume of the solution in milliliters, and we converted the milliliters to liters. If we take the moles of HCl, 0.99 moles, divided by the volume of the solution in liters, 0.0909 liters, we get that the solution is 11 molar. Let's use this same data now to calculate the molality of this solution. Again, it is noted that we'll make the assumption of 100 grams of solution. Based on that assumption, we can conclude we have 36 grams of HCl. And if we have 100 grams of solution and 36 grams of HCl, we can conclude that we have 64 grams of water. To calculate molality, we need moles of HCl divided by kilograms of solvent. The solvent in this case is water. It is safe to assume that water is the solvent unless the problem indicates otherwise. Again, the 36 grams of HCl is 0.99 moles as we divide by the molar mass. Now we've got to take the 64 grams of water and convert it to kilograms. There are 1,000 grams in 1 kilogram, so we'll take 64 grams divided by 1,000 grams and get 0.064 kilograms. Lastly, we'll take 0.99 moles of HCl, divide by 0.064 kilograms of H2O, and we'll obtain an answer that indicates our solution is 15 molal. Converting between concentration units does not involve complicated math, but it does involve a large amount of thought about the given information, and the key is being able to take the given information, as we have done here, and convert it to grams of solute, grams of solvent, and grams of solution. Once you've obtained those three masses, calculating any of the concentration units we have discussed is fairly simple. Practice makes perfect for this particular technique. Your textbook, homework, quizzes, and exams provide an ample proving ground for doing these calculations. Be sure to consult your textbook and your instructor should you need further clarification on this topic.